Okay, so we have the very last talk of the session. It's going to be given by Rui. It's about hybrid meta-learning framework for adaptive safe controller synthesis of dynamic systems.
Okay.
The floor is yours.
Thanks for your introduction, and good evening, ladies and gentlemen. And today I will present my work titled Hybrid Meta-Learning Framework for Adaptive Safe Controller Synthesis of Dynamical Systems. And this is a joint work with my collaborators from Zhejiang Scientific University. Okay, let's begin. Okay, let's show you the background. Cyber physical systems are increasingly deployed in safety-critical applications, such as the self-driving cars, air traffic control system, and the train control systems. And in these scenarios, failures can lead to severe consequences. As a result, controllers for such systems are required not only to achieve performance objectives, but also to provide strong safety guarantees. Formal safety verification offers a principled way to ensure that a system can avoid unsafe states. However, it faces some challenges, especially when the system becomes more complex and more high dimensionality. And this challenge motivates the need for adaptive and efficient safety controller synthesis methods, which is the focus of this work. So let me briefly review the existing approaches. Firstly, I will introduce the learning-based safe controller synthesis. And in this kind of approaches, the neural controllers are learned together with barrier certificates, often combined with counter example guided synthesis. And an example is a fossil. But this method provides strong safety guarantees, but they typically require solving each new system from scratch, which makes them inefficient when system dynamics vary. So meta-learning is introduced in this kind of problem. And the first kind of the meta-learning is called gradient-based meta-learning. And an example is ML. So this kind of method enable fast adaptation and through shared initializations. While this method have been applied to control and stability certification, a single initialization is often insufficient for safety controller synthesis across systems with different dynamics and safety constraints. And in the last, I will introduce the model-based meta-learning. And this is kind of meta-learning to learn task embeddings to capture task structure and enables efficient task representation. However, this method is not usually designed for formal safety guarantees. And overall, all of these three kind of approaches cannot simultaneously achieve fast adaptation, task-specific synthesis, and formal safety guarantees. And this gap motivates the hybrid meta-learning framework. And based on above, we make the following key observation. Safety controller synthesis tasks are not independent at all. Although system dynamics and safety constraints vary, they share latent structure that can be learned and reused across tasks. And gradient-based meta-learning enables fast adaptation, but it treats tasks in a task-agnostic manner and relies on a single initialization. On the other hand, model-based meta-learning can capture task-specific structure through embeddings, but it's typically not designed for safety guarantees. So this leads to our motivation. We want to learn task structure for fast adaptation while enforcing formal safety guarantees. And this figure illustrates how we combine the model-based and gradient-based meta-learning. And in the left part, it is corresponding to the model-based meta-learner. which learns the task embeddings from the trajectory data. And these embeddings capture latent structure shared across the safety controller synthesis tasks. And the red part is the gradient-based meta-learner, and where the controller network and the barrier networks are adapted, conditioned on the task embedding learned before. And let's see the training and the adaptation process. The black arrows indicates the training process. And in the meta training is on multiple tasks, where both the embedding network and the controller network and the barrier network, their parameters are optimized. And the red arrows indicates the adaptation for a new system. We just use the limited data and enables fast adaptation to a new system. And then we follow it is followed by a formal verification to ensure safety. And now we considered a controlled continuous dynamical system with a vector field f, and this. And the system evolves according to these equations. And the u is the control input, which is given by the feedback controller. And the system is defined over domain xd, and initial set xi, and unsafe set xu. And the problem, or our objective, is to synthesize a controller such that all trajectories of the system that start from the initial region, it cannot enter the unsafe region. And we guarantee the safety. To guarantee the safety, we adopt the barrier certificate or the control barrier certificate. And a barrier certificate is a real valued function. And as you can see, the barrier function separates the initial set from the unsafe set. And it enforces forward invariance through a Lie derivative condition, specifically in the right of this slide. The barrier function is non-positive over the initial set, and it is strictly positive over the unsafe set. And its Lie derivative is strictly negative over the zero level set. And the control barrier certificate provides a sufficient condition for safety, which we use throughout our framework. And then it goes to our method. In the top of the slide, it is the model-based meta-learner. And in this one, the key idea is to represent each safety controller synthesis task using an embedding learned from the trajectory data. For each system or for each task, we generate the trajectory sequences consisting of the x, which means the system states, and the u, which means the control input, and the r means the reward signal that reflect the distance to the unsafe area. And then the sequences are processed by an LSTM network, and the final hidden state of the LSTM is the task embedding we use. And this embedding captures the task-specific information about the system dynamics and the safety constraints. And importantly, this embedding is not used to directly predict the control action. Instead, it conditions the synthesis of both the barrier and the control network in the next stage. And although each task has its own embedding, the embedding network is just like the LSTM network itself. It is shared and meta-trained across all the tasks. So let's go to the gradient-based meta-learner. Yes, it's done. After giving the task embedding, we synthesize both the barrier and the controller network using gradient-based meta-learning. And the embedding is concatenated with the system state X, and they are used as the input to both networks. And in the inner loop, the two networks parameters are adapted to a specific synthesis task by minimizing a task-specific loss that encodes the barrier certificate condition that we mentioned above. And during the outer loop, the meta parameters are optimized across tasks so that only few gradient steps are required to adapt to a fast adaptation. And in this way, the gradient-based meta-learning enable efficient synthesis of task-specific barrier certificates and the controllers conditioned on the learned task embedding. So this is the new task adaptation phase. When given a new system, we first collect a small amount of the data and use those data. We generate the sequences and extract a task embedding using the learned embedding network. And then, starting from the meta-learned parameters, we then perform a few gradient steps to adapt both the barrier certificate network and the controller network. And importantly, this kind of process does not require training from scratch, not like the learning-based approach. And it demonstrates that the meta-learned initialization and task embedding reduce the number of gradient steps for adaptation for new system. And finally, we ensure formal safety guarantees through verification. Learning alone is not sufficient for the safety-critical systems. And barrier certificates provide a sufficient condition for safety, but we still need to verify whether a learned candidate actually satisfies the condition over the state space. And given after the synthesis of the controller network and the barrier certificate after the synthesis of the control and the barrier certificate network, we encode the barrier condition into the SMT constraints, and we use the real solver to verify them. And if the solver find the counterexamples, you will sample the If the solver find counterexamples, then they will be used to generate additional training samples, and the barrier network and the controller network will be refined accordingly. And this kind of process will be repeated until in a counterexample guided manner until all the conditions are formally verified. And safety in our framework is not based on empirical testing or simulation, but it is guaranteed through formal verification. And this is the experimental evaluation. We evaluate our proposed framework on a set of benchmark systems, including 2, 3, and 4-dimensional systems. And we compared our method against the fossil tool and the MML-based method. And the table reports the success rate and the computation time for each method. As we can see, our method achieve a higher success rate and while requiring less computation time. And these results demonstrate that the proposed hybrid meta-learning framework improves both efficiency and the reliability in adaptive safe controller synthesis. So to conclude, we propose a hybrid meta-learning framework for adaptive safe controller synthesis. And by combining model-based and gradient-based meta-learning, our method enables fast adaptation to new systems while capturing shared structure across the tasks. And the safety in our framework is formally guaranteed through SMT-based verification. And overall, this work demonstrates that meta-learning and formal verification can be effectively integrated to address adaptive safety synthesis problems. Okay, that's all. Thank you.
Yeah, so I think we have, it was a bit short, in the sense that we have like, I think about 10 minutes or so if anybody want to follow up with questions. Yeah.
No. Hello. In the evaluation slide, what was the round? What does that represent? The round quantity.
This?
Yeah.
Round means the verification run by DRIL. The DRIL. We use DRIL, and round means that after training we use DRIL to verify, and if we find the counterexamples, we will do the training and verifying, and that's
okay. So the number of times you have to do this loop.
What?
The number of times you have to do this?
Time?
Yeah, the number of times you have to go back and forth between the training and the verifying.
I'm sorry?
So maybe like the I don't know, if you mean like the number.
I mean, if I understood right, you have to have the interactions you have to do with.
Yeah. So is it like the number of is the number of interactions like the number of counterexamples maybe from SMT?
I still don't get what you mean.
I mean, yeah. So we just want to know what round means. So
round means just as I said. After we trained, we get the two networks. We use the DRIL to verify, and then if the round one means there is no counterexamples during the verify, we just get the red candidates.
That would be 0.
That will be 1.
1. Okay.
Yes.
Okay. So I think that's it. But what is this then?
This like the ML-based approach cannot converge. Yes.
Okay. I see. All right. Okay, so it's only not so many. It's all very small, right? All of these numbers.
Oh yes.
Only like 1.
Yes, because the FOSL 2 is a state-of-the-art learning-based approach to the control synthesis control.
So most of the time is spent on the solvers or on the
training and
mostly on the
time
training.
is including the training time and the verify time.
Yeah, but how much time spent by the SMT solvers?
Maybe just a
little bit.
A little bit, yes. Okay. Most time in our method, most time is the training, yes. And but for FOSL, maybe some the verify time and the training time maybe a half.
Okay.
Thank you. So I have maybe 2 questions. So the first one is: so you said you use DRIL, so there is some it's not precise, right? So does that occur the imprecision somewhere? Is it a bottleneck?
What?
DRIL is not precise, right? It is not exact. It's using some approximation.
No, I just use DRIL.
Okay, so you don't. Okay, so you use DRIL, but is there any problem with its imprecision in your approach?
What?
Is there a problem that DRIL is not precise in what you're doing, or do you need to somehow handle the imprecision, or
is that approximation or
approximation?
Yeah, I don't know. Is it?
So DRIL, it's not precise. It has some epsilons, right?
I don't know. DRIL is not precise.
Okay.
Okay, so maybe another question. So you're talking about synthesis, but there is another approach is like, so you're synthesizing safe controllers, right? And another approach is like to use an unsafe controller, but using some kind of shielding. Have you compared with these approaches?
No, I just compared to this kind of two approaches to synthesize the safe controller.
Okay, thanks.
So shielding is like instrumentation?
Well, you're checking what's happening and detecting the unsafe behavior.
Okay, when it's unsafe, then you just like, okay, then you protect it. Okay. All right, okay. I have a very general question because I was a little bit confused because I don't know, maybe I didn't really understand at the beginning.
Yes.
What do you mean when you say, what is really the difference between model-based and gradient-based? What is model-based here?
Okay. Here?
Yeah.
Gradient-based meta-learning is a
well, I know gradient-based,
yes.
but what is model-based?
It's kind of, it's also called black box meta-learning. And you have a set of tasks, and the model-based meta-learning will extract embedding from the task and use the embedding to predict the network.
Okay.
Yes, that's the model-based meta-learning. It is not optimized. It is not optimization based. It is based on the model, the network to generate the task embedding and use the task embedding to do what you want to do. And that's the model-based meta-learning.
And usually there, so and gradient-based is basically just using some neural network, something like that, or some kind of local search, or that's what it means here.
Actually, I didn't know that so much. I just know the model-based meta-learning is not really used in the safety guarantees, this kind of area.
More questions? I guess if we don't have questions, we are off for an early coffee break. All right, thank you so much again.
Okay, thank you.